Good morning, students. In this video, we are going to find out the interferences bandwidth. Sir, interferences means alternative bright and dark fringes will be occurred due to the superimposition of two light sources. By this experiment, we are going to find out the two consecutive bright or two consecutive dark fringes of width. So that should be called as bandwidth. The experimenter's motto is to determine the bandwidth of the fringes. Okay. What is Young's double slit experiment? For what purpose we are using this type of experiment? We already know the three techniques to obtain the coherent sources. One is intensity or amplitude division, and then second one is source image technique, and then third one is wavefront division. In a wavefront division, we analyze the double slit technique. When a single monochromatic source produces the coherent sources with the same phase difference, frequency, waveform, and as well as intensity or amplitude. So that's why we are using the double slit techniques to measure to get the expression of bandwidth. Okay, let me see how the experimental setups are arranged by the British scientist Ames. Sir, the source is placed in some pointer. In front of the source, the scientist placed one slit. It makes a two fine hole which should be act as a slit. So this is a slit S1 and then S2. The property of the slit S1, S2 has the fine width. The width of the slit is S1 and then S2 has a slit width of 0.03 millimeter. And also the two slits are separated by a small distance that should be indicated by the small d. The d value is 0.3 millimeter. 0.3 millimeter. The sources produces a spherical wavefront as well as we discussed. The single source produces the wavefront through the slits. And before that, the scientist placed one screen beyond the slit at the distance of capital D. He placed a screen. That's it. This is the experimental setup from the Young's double slit. What will happen? The monochromatic source of the spherical wavefront produces a wave through the S1 and then S2. We know very well. From the S1 and S2, we are getting crust and crust pattern or trough and trough pattern. It produces the constructive interferences. Otherwise, crust and trough or trough and crust pair produces the destructive interferences. Let me consider with respect to the path and then phase difference at the point of P in the screen. The S1 slit produces the light rays and it will be impinged on the screen at the point of P. And then S2, from the S2 slit, the light rays is moving and incident on the point P. At this point on the screen, it may be in the fringes of bright or dark, we don't know. Okay, sir. The center of the two slits is taken as center point of C, and then midpoint of the screen is indicated as O. So this should be connected by the dotted line. This is the setup of Young's double slit experiment to determine the bandwidth of the fringes, interferences pattern. Now I am going to measure the value of Y with respect to the bright or dark fringes, and finally we are going to get the expression of bandwidth. Okay, students? Okay, let me see. to get the path difference first, and then we will find out the bandwidth. From the slit of S1, the light is impinged at the point of P, and then S2, the impinge at the point of P. Students, you get the attention at this point. See here, the path length of the S1P and then S2P is equal. Not possible, sir. The path difference is differing. S1 of P, S1P is not equal to S2P. So there is certain path differences occurring. Now I am going to find out the first path difference. How to measure the path difference? Listen here. I am just simply drawing a perpendicular line from the point of S1 to S2P. So now I am going to draw the perpendicular line from the S1 to the S2P. It meets a point of M. Am I right? So now the S1P is equivalent to MP. Am I right? So S2P minus of MP gives the path difference value, that is S2M. This is my path difference value. It is indicated by the term of del. Finally, the path difference has been deducted. What is the value of path difference? S2M. So, by this expression, I am going to get the distance between the center of the screen and then brighter dark fringes at the screen of P. So, by using the path difference del, I am going to find out the expression value also. Now the path difference is identified as S2M. What is the value of S2M? How will we detect the value of S2M? Okay. Now the center point of the slit is C and then midpoint of the screen is O. At the point of P, we detected certain point with respect to the phase and then path difference. So the angle of PCO, otherwise the angle of OCP, the angle of OCP is equivalent to theta. It creates an angle of theta. If suppose the angle of OCP is theta, then the angle of S2, S1, M also theta. Am I right? These are same and similar triangles. So the angle of S2, S1, M is equivalent to theta. By equating these two angles or these two triangles, we will get the solution of bandwidth. Okay. Now I am going to compare these two triangles. For finding the path difference, del is equal to S2M. Okay. What is the triangle? The triangle of OCP and then the triangle of S2, S1M. Okay. Let me discuss. Here, the angle of OCP creates an angle of theta. So, the value of triangle of OCP, tan of theta is equal to, because we know the value of opposite side and then adjacent side. So, OP is the Y and then the distance between the slit and then screen is D. So, tan theta is equal to OP divided by OC. So, what is the value of OP? Y, and then what is the value of OC? D. So, the tan theta equal to Y by D. Okay, students? And then next, what is the another triangle? S2, S1, M. So, from the triangle of S2, S1, M, sin theta can be going to find out. Listen, students, for the angle is very small, sin theta and then tan theta is equal, you know? Yes. That's why in the angle of S2, S1, M, I am going to find out the sin theta value. So, sin theta is equal to opposite side divided by hypotenuse. So opposite value is that here is the theta. The opposite value is S2m. S2m divided by the hypotenuse value is S1d. Sorry, S1 and S2. So the sine theta is equal to S2m divided by S1 S2. What is the value of S1 S2? The distance between the two slits is called d, small d. So sine theta is equal to S2m divided by small d. What is the value of path difference? Path difference del is equal to S2m. Finally, we are going to derive this one. So S2m equal to d sine theta. Am I right? Otherwise, the path difference del is equal to d sine theta. For our consideration, here the triangle of OCP and then triangle of S2 S1m has a small angle. So let me consider tan theta equal to sine theta equal to theta. That means the theta value becomes y by d. Am I right? Here the path difference del is equal to d into theta. Now the path difference del is equal to d into theta. What is the value of theta? So theta is equal to y divided by d. Now I am going to substitute the value of theta in the path difference. So del is equal to d into y divided by d. What is the value of small d? The distance between the two slits. What is the value of capital D? The distance between the slit and the screen. What is the value of y? From the midpoint of the screen at the point of P. So this should be a value of P. Now I am going to simplify this equation, but we know the path difference values of constructive and destructive. If suppose at the point of P there must be a bright fringes. Sorry sir, there might be a dark fringes. What is the path difference for bright and dark fringes? Sir, the path difference expression for bright fringes is del is equal to n lambda for bright fringes. Sir, the dark fringes path difference del is equal to 2n minus of 1 lambda by 2. This is for dark fringes path difference condition. Now I am going to substitute the value. If suppose at the point of P there might be a bright fringes, then del is equal to n lambda equal to y into d by d. Sir, this is a condition for bright fringes. Now I am going to find out the width of the fringe from midpoint of screen to at the point of P. So that should be indicated by the value of y. So y is equal to, by interchanging this equation, d by d n lambda. Am I right? This is a condition for bright fringes alone. Suppose at the point of P there might be a dark fringes. So the path difference value is 2n minus of 1 lambda by 2 equal to y into d by d. So the width of the fringe y is equal to d by d 2n minus of 1 lambda by 2. This is for the destructive interferences. Destructive interferences. This is for constructive interferences. Okay students, now we have the value of width of the fringe. Now I am going to find out the bandwidth value. What is the bandwidth? How will you define? The bandwidth is defined by the consecutive of two bright or dark fringes. The value is bandwidth. Am I right? So the bandwidth will be calculated by the two adjacent to or two successive bright fringes. Now the bright fringes condition is y is equal to d by d n lambda. This is my first fringe. Suppose the next fringe is y is equal to, that is yn plus 1. This is the nth fringe. This is the second order. So y of n plus 1. If you are supposed to give the value of n equal to 1, 1 plus 1 equal to 2. There is the second right fringe. So y of n plus 1 is equal to d by d n plus 1 into lambda. Am I right? So now I am going to find out the bandwidth value. So bandwidth is represented by the term of beta. So y of n minus 1, n plus 1, y of n plus 1 minus of yn. That is final fringe minus of initial fringe. So substitute the value of y of n plus 1 and then yn. D by d n plus 1 of lambda minus, what is the value of yn? D by d n lambda. Am I right? Okay. But simplify this equation. The common values are d by d and then lambda is common. So next n plus 1 minus of n. It will be cancelled of minus 1 and then plus 1. Finally we get beta is equal to d by d n lambda. This is the bright fringes of bandwidth condition. This is the bandwidth expression. Beta is equal to d by d n lambda. Very important relation. So from this relation, if you are supposed to decrease the value of small d, what is the small d? The distance between the two slits. If you are supposed to decrease, the bandwidth will be increases. Suppose the distance between the slit and the screen will be increases. That is, a capital D is increases, beta also increases. Suppose the wavelength of the source is high, then the bandwidth also high. So finally, to get the saturated and then conditional bandwidth for the interferences, to produce the maximum or to use the maximum wavelength. And the second one, how far you are maintaining the screen distance. And the third one is the distance between the two slits should be very narrow. These are all the conditions to achieve the saturated bandwidth. Okay, students.